In this lecture, we will learn advanced concepts for system of linear equations where the number of equations may or may not be equals to number of unknowns, and that's why we denote number of equations by m and number of unknowns by n. And for this system of equations, we will learn the concepts of consistency, that is when this system of linear equations has solution, inconsistency when this system of linear equations does not have a solution, number of solutions, that is when the system of linear equations has solution, how many solutions are there, and out of the solutions, how many solutions are linearly independent. If you want to learn about linear independence, then you can watch my video on linear independence of vectors. Here, because our solutions will be vector x, so linear independence of our solutions will be same as linear independence of vectors. So our system of linear equations is given like a11x1 plus a12x2 plus dot 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 plus a1n xn equals to b1, and similarly we are given m equations, and in matrix form that can be written as ax equals to b. Here A is the coefficient matrix of size m by n. We have m rows corresponding to m equations, and we have n columns corresponding to n variables. X denotes vector of unknowns and its size is n by 1. B denotes vector of constants and its size is m by 1. Here note that our unknowns x are written as vector of size n by 1. So linear independence of our solution will be same as linear independence of vectors. Now for this system of equations ax equals to b, if b is not equals to 0, and here note this 0 vector is also of size m by 1. If b is not equals to 0 vector, then the system is called non-homogeneous system of equations, and if b is equals to 0 vector, then the system is called homogeneous system of equations. Now both of these cases can be further divided into three different cases. First, where number of equations is equals to number of unknowns. Second, where number of equations is less than number of unknowns. Such system is called underdetermined system of equations. And third, where number of equations is more than number of unknowns, and such system is called overdetermined system of equations. Now let's first consider non-homogeneous system of equations, that is where vector b is equals to non-zero vector and number of equations is equals to number of unknowns. In this case, because m is equals to n, our coefficient matrix will be a square matrix. So we can find determinant of A. So we can use the determinant method to analyze this system of equation for consistency, inconsistency and number of solution. And this I have done in a separate lecture. If you want, you can watch that lecture to understand this case in more detail. Next, we consider a non-homogeneous system of equations where number of equations is less than number of unknowns, that is m is less than n. Such system is called underdetermined system of equations, and if such system is consistent, then it has infinite solutions. So let's see this using an example. So let's consider the system of equations x plus y equals to 3. Here we have one equation, so m is equals to 1, and there are two unknowns x and y, so n is equals to 2, and here we see that m is less than equals to n. Now we also know that x plus y equals to 3 is equation of a straight line in 2D plane, and if I plot that line, then I get a line like this, and we know that every point lying on this line satisfies equation of this line. So x plus y equals to 3 is consistent and has infinitely many solutions. However, if we have a system of equations like x plus 2y plus 2z equals to 2 and x plus 2y plus 2z equals to 4. Here note that we have two equations. So m is equals to 2 and we have three unknowns x, y and z. So n is equals to 3. Here we have m less than n, but this system of equations is inconsistent because we know that a linear equation in three variables represent equation of a plane in three-dimensional space, and these two equations, and here the coefficients of x, y and z are equal, but the constant term is different. So these two equations represent two parallel planes in 3D space and they do not have any common point. So there is no set of values of x, y and z that will satisfy both the equations. So this system of equations is inconsistent. The third case for non-homogeneous system of equations is when m is greater than n, that is number of equations is greater than number of unknowns. Such system is called overdetermined system. Here note that if all m equations are not linearly independent, and we will see how to find number of linearly independent equations in the given equations, but if all m are not linearly independent and if the number of linearly independent equations is greater than number of unknowns, then such system will be inconsistent, means there will be no solution. And if the number of linearly independent equations is less than or equals to number of unknowns, then the system will be consistent. Let us understand that using an example. Say we are given a system of equations as x plus y equals to 3, x minus y equals to 1 and 2x minus 5y equals to 10. Here note that the number of equations m is equals to 3 and number of unknowns n is equals to 2 and m is greater than n because we have equations in two variables. Each of them will represent a straight line in 2D plane. Let's call these equations 1, 2 and 3, and if I plot them on a 2D plane, then I will get these lines. Here note that the equation 1 is denoted by line number 1, equation 2 is denoted by line number 2 and equation 3 is denoted by line number 3. And because the solution of a system of equations in two unknowns is a pair of numbers x and y that satisfy all three equations, and because on these three lines we do not have any common point which satisfies all three lines, means there is no pair of x and y that will satisfy all three equations of this system simultaneously, and hence we do not have any solution, and that implies that the system of equations is inconsistent. So in this case, all three equations are linearly independent. Therefore, the number of linearly independent equations is more than number of unknowns. So this system of equations is inconsistent. Next, let's consider an example where the equations are linearly dependent. Equations are x plus y equals to 3, x minus y equals to 1, 3x minus y equals to 5. And let's call them 1, 2 and 3. And here note that in this case also the number of equations m is equals to 3 and number of unknowns n is equals to 2 and m is greater than n. Now if I plot these three lines in 2D plane, then I get equation 1 is represented by the line number 1, equation 2 is represented by line number 2, and equation 3 is represented by line number 3. And here note that all three lines intersect at a common point, and that is the point that satisfies equations of all three lines. That means there exists a pair of x and y that will satisfy all three equations, and that will be the solution of this system of equations. And if we note the coordinates of the common point are 2, 1, that means x equals to 2 and y equals to 1 is the solution of my system of equations. And if we substitute these values of x and y in all three equations, then all three equations are satisfied. That means this system of equations, despite having m greater than n, is consistent. And if I look carefully, the equation number 3 can be obtained by multiplying equation 1 with 1 and adding equation 2 multiplied by 2. That gives me 3x minus y equals to 5, and that is nothing but my equation number 3. So here these three equations are not linearly independent, they are rather linearly dependent, where third equation can be written as linear combination of equation 1 and equation 2. So if in the case where m is greater than n but number of linearly independent equation is less than m, then the system may be consistent. Now, generally, it is not easy to identify linear dependence of equations just by observation. So now, how do we in general know whether a system of equations where number of equations and number of unknowns are different is consistent or not? And for that, we use the rank method, and rank method is applicable for all the cases of system of linear equations, that is for both non-homogeneous as well as homogeneous system of equations, and for all the cases of number of equations and number of unknowns, that is if number of equations is less than number of unknowns, when number of equations is equals to number of unknowns, and when number of equations is greater than number of unknowns, that is for underdetermined system and perfect system and overdetermined system. And I will explain all the properties of rank method for all these cases one by one. So for a non-homogeneous system of equations given as ax equals to b, where m is number of equations and n is number of unknowns, for that we define two ranks: rank of coefficient matrix, let's call that R, equals to rank of A, which is m by n matrix, and R prime be the rank of augmented matrix of A, and augmented matrix of A is obtained by making the constant vector B an additional column of A, and that is written like this. And note that rank of a matrix cannot be greater than number of rows or number of columns of that matrix. So R will be less than or equals to smaller of m and n, and R prime will be less than or equals to smaller of m and n plus 1. Here note that the augmented matrix of A will have m rows and n plus 1 columns because we have included the coefficient vector as an additional column to get augmented matrix of A. Conceptually, the rank of coefficient matrix, that is R, is equals to number of constraint unknown variables in our vector X, and by constraint unknowns we mean the unknowns that have to be solved using the system of linear equations. And the rank of augmented matrix, that is R prime, is equals to number of linearly independent equations in our given system of equations. Now if R, that is rank of coefficient matrix, is not equals to R prime, that is rank of augmented matrix, then the system of equations will be inconsistent, means no solution will exist. And if R is equals to R prime, then the system of equations will be consistent. In fact, we can learn more than just consistency from these ranks, and that is if the ranks are equals to n, that is number of unknowns, then there will be a unique solution, and if the ranks are less than n, then there will be infinite solutions, and there will be n minus r free variables. By free variables, we mean that they can take arbitrary values, and the r constraint variables will have to be solved in terms of the constants and these free variables. Here, if we consider a system of equations consisting of one equation in two unknowns, then for this system of equation, m is 1, n is 2, and if I write that in the matrix form, then this equation will be 1, 1, x, y equals to 3. Here coefficient matrix is of size 1 by 2, the x vector is of size 2 by 1, and b is of size 1 by 1, and here the rank of coefficient matrix R will be just 1, and the rank of augmented matrix, that is R prime, also will be 1, and we have the case of R equals to R prime less than n. So in this case there should be n minus R, that is equals to 2 minus 1, 1 free variable, R equals to 1 constraint variable, and as we already know, this system of equation is infinite solution. So if I choose say y to be free variable, then I can find infinitely many solutions in terms of the constant 3 and y, and they will be x equals to 3 minus y. Here I can choose any arbitrary real value for y, and in terms of y and this 3 I can find value of constraint variable x. Next we move to the case of homogeneous system of equations where b is equals to 0. So our system of equations will become a into x equals to 0, and here m is number of equations and n is number of unknowns, and in this case the rank of coefficient matrix, that is R, will be equals to rank of augmented matrix, that is R prime, because addition of this column with all entries equals to 0 does not change rank of augmented matrix. And here also the R will be less than or equals to smaller of m and n, and R will be number of constraint unknowns. By constraint unknown, we mean that these unknowns have to be solved using our system of linear equations. And because for the homogeneous case R is always equals to R prime, the homogeneous system of equations will always be consistent, and therefore in the case of homogeneous system of equations, we are more interested in when we only have a trivial solution, that is solution where all x's have value equal to 0, and when our system of equation will have non-trivial solution, that is when do we have non-zero solutions for our system. So if the rank of coefficient matrix is equals to n, that is number of unknowns, then there will be a unique solution, and this unique solution will be the trivial solution, that is values of all the unknowns will be 0. Now if rank is less than n, there will be infinite solutions for our system of equations, and there will be non-trivial solutions also. So the condition for having only trivial solution is rank of the coefficient matrix should be equals to number of unknowns, and condition for having non-trivial solution is rank of the coefficient matrix should be less than number of unknowns. Now in this case where rank of coefficient matrix is less than number of unknowns, we will have n minus r free variables, that is these variables can take arbitrary values, and there will be r constraint variables, and these constraint variables have to be solved in terms of free variables, and there will be n minus r linearly independent solutions. And by linearly independent solutions we mean that these n minus r solutions cannot be written as linear combination of each other, and remaining infinite solutions can be written as linear combination of these n minus r solutions.